HS 3.2, essentially there's three ways of looking at the liver. You can look at it in terms of anatomy, where the blood flows from the large branch of the portal vein, hepatic portal vein, and the hepatic arteries to the central vein. That's the blood flow, the pure blood flow through the sinusoids into the central vein. That's the classic hepatic lobule. You can also look at it as a portal lobule. And in terms of the portal lobule, what that is, basically the blood flows outwards, because remember the blood is produced by the hepatocytes and flows out to the branch of the bile canaliculi to flow into the bile duct. You can also look at it as a portal acinus, and this is where blood flows inwards, just like the hepatic lobule, but it supplies the tissues. So it supplies the hepatocytes here, and supplies them as you get closer and closer to the central vein. And as the blood moves from the outside to the inside, it essentially creates three zones: zone 1, zone 2, and zone 3 as you move closer inwards. So let's look at the portal acinus blood zones. Well, zone 1 gets the most oxygenated blood, and therefore the hepatocytes in zone 1, they're used for oxidative metabolism, drug reactions, and bile synthesis. Whereas zone 3, which is the cells nearer the center, the hepatocytes nearer the center, they're the least oxygenated, and therefore if you have hypoxia, then they'll get barely any oxygen at all, so they'll be very damaged by hypoxia. In terms of liver functions, these are the overall functions of the liver. First of all, metabolism. Well, the liver is involved in carbohydrate metabolism because glucose homeostasis. It's involved in fat metabolism by synthesizing lipids, handling fats, and synthesizing cholesterol. It's involved in protein homosynthesis, and it's involved in detoxification. That's one of the main functions. What does detoxification involve? Well, it involves drug elimination, biotransformation to detoxify drugs, and ammonia elimination. Also, the liver produces bile salts from cholesterol. So cholesterols are turned into bile acids, which then become bile salts. It forms them and secretes bile salts for fat metabolism. Fat absorption even. And the liver also has an immunological function. So the functions of the liver: metabolism, protein and hormone synthesis, detoxification, bile salt production, cholesterol synthesis and conversion, and an immunological function. So first of all, let's look at glucose homeostasis. Well, the liver is for glucose homeostasis. If the glucose is too high, then you're going to get neuroglycopenia, which is low glucose in the brain. And if the glucose goes if you get too low, you get neuroglycopenia. And if it's too high, you'll get tissue damage. In the fed state, glucose is you got food in the gastrointestinal tract, so you're going to want to store that glucose somehow. So in the fed state, the glucose is taken up by the hepatocytes and it's stored. It can either be stored in the liver as glycogen, or it can be stored in the muscle as fat. However, in the fasted state, you don't have any food, so you need to make more glucose. How are you going to do that? Well, in the liver is glycogenolysis, which is the breakdown of glycogen into glucose via glucose 6-phosphatase. And in the muscle, well, muscles don't have glucose 6-phosphatase. So gluconeogenesis happens from amino acids, lactate, and glycerol to make glucose. And ketogenesis happens, which is the fatty acids are oxidized to acetyl-CoA, which becomes ketone bodies through ketogenesis for energy. And this is a glucose sparing reaction, because if you're using the ketone bodies for energy, then it's sparing glucose. And if you make gluconeogenesis, if you make glucose and spare it, then it leaves glucose for the brain. Well, one thing you might ask is, why can't you use the ketone bodies for the brain? Well, ketone bodies and fatty acids cannot be used by the brain because they can't cross the blood-brain barrier, whereas glucose can. So let's have a look at this ketogenesis thing going on here, the conversion of fatty acids to acetyl-CoA and ketone bodies. Well, fatty acids pass through the beta oxidation cycle. And the beta oxidation cycle, this produces reduced NADH and reduced FAD, which go on to the electron transport chain for ATP production. Beta oxidation also converts them. They can also be converted to acetyl-CoA. Instead of the being converted to beta oxidation, instead of the beta oxidation pathway, they can be converted to acetyl-CoA. And then acetyl-CoA is converted to ketone bodies and is used by tissues, sparing glucose for the brain.